Hi, in today's video we're going to be talking about how to transform an alcohol into another functional group. In this case, it's an alkene. So one of the things that we're going to be focused on in the next couple of videos is the fact that carbocations are generally avoided in organic reactions because they can undergo all sorts of different types of reactions, as you've seen in previous videos. So let's look at a reagent that can dehydrate or remove H2O from a molecule very selectively. So if we take, for example, isopropanol, an alcohol like isopropanol, we can treat this with POCl3. So POCl3 is also called phosphoryl chloride or phosphorus oxychloride. We can also just simply call it POCl3. And we're also going to use a base. This is a pretty mild base called pyridine, and you'll see the structure in just a moment. So this is a net dehydration reaction because ultimately you lose an equivalent of OH and H, and this again gives you the loss of water. And just like when you're dehydrated in the desert, loss of water is also called dehydration in an organic reaction. So in this first case, I'm going to show you this reagent, and I want to point out that when you are trying to study these types of reagents, I would like you to make 3 note cards for these reagents. One where the reagent is missing. So in this case, you're going from an alcohol to an alkene, and you're quizzing yourself about what reagent is missing. Another where the product is missing. So in this case, again, you have a blank spot where the product is, and so the opposite side of the card, you'd show the product. And the third one is where you'd have the starting material missing. And if you can do all 3 of these transformations, then you'll be able to convince me and convince others that you fully understand how and when to use this particular reaction. And so these types of note card strategies are really useful. And I won't always highlight which note cards to make in the future, but generally you make a note card for the reagent, a note card for the product, and a note card for the starting material for each of these reactions. So let's move forward into how this reaction actually works. Let's look at the mechanism. So if you start with your alcohol and your phosphorus oxychloride, the alcohol is going to act as a nucleophile, and it's going to displace this phosphorus chlorine bond. And so you're going to obtain this type of structure where you have oxygen with a positive charge and the chloride. Here's where your base comes in for the first time. You'll see it come in a second time as well. So pyridine is going to act as a base, and it's going to abstract this proton to give you now this neutral oxygen-containing species. And you'll see that you form pyridinium chloride, so this is now a relatively stable salt. So this molecule is now set up such that this oxygen species is now a good leaving group. And so if the base is now going to deprotonate on the carbon alpha to the leaving group, that's going to undergo an elimination reaction. And in this case, this particular elimination reaction is an E2 elimination reaction. I'll point out that this is a good leaving group because you have resonance structures for this oxygen, so this negative charge can actually be delocalized across both of those oxygen atoms. So it's an E2 mechanism, so let's again remind ourselves of the implications of an E2 elimination reaction. We have to have the anti-periplanar orientation, so if you need a refresher on that, go back to that previous video on E2 elimination mechanisms. But let's look at these 2 alcohols here. So we'll treat each with phosphorus oxychloride and pyridine. Sometimes I'll abbreviate pyridine as PYR. And again, if you ever have a question about that, ask me what PYR is, and I'll say it's pyridine. And keep in mind that pyridine is a base. So in both of these cases, this reagent is going to render this hydroxyl group, this alcohol, into a leaving group. And so we need to look to what protons are anti-periplanar to this leaving group. So in this first example, you have 2 protons that are anti-periplanar. In this other example, you actually only have 1 proton that is anti-periplanar. This one's coming out of the plane at you, this one's going away. Again, these 2 are syn to each other, and so that is not as favorable for an elimination reaction. So you would predict that if you were to treat this alcohol with phosphorus oxychloride and pyridine, you'd obtain the major product as this more substituted or more stable alkene, because again, there's this proton you could abstract to generate the more stable alkene. In this case, you'd only obtain this product, not as the major, but as the only product, again, because the anti-periplanar hydrogen is not the most favorable would not generate the most favorable alkene, but it's the only one that's available to react. Thank you for your time, and I look forward to seeing you next video.